Welcome back to this lecture on the computational complexity of matrix algorithms. In this segment, we're going to look at a different problem, namely matrix addition. So how do we define this problem? Well, the problem takes two inputs, two matrices A and B. Now, these matrices must have the same dimension. Since we're only dealing with square matrices in this lecture, that means the matrices A and B must have the same number of rows. And the result, or the solution to this problem, is a third matrix C that has also the same dimension as A and B, and every element in C is the sum of the corresponding elements in A and B. So for example, the top left element in C is going to be the result of adding the top left element in A to the top left element in B, and so on for all of the elements of the matrix C. So, here is a description of an algorithm to solve this problem. Given two square matrices as input, A and B, it is not stated here, but they must have the same size. The function returns another square matrix C that is the sum of A plus B as we just defined. So let's write down the pseudocode for this algorithm. It starts with a keyword function since the algorithm returns a matrix. The name of the algorithm is short but meaningful, like matrix add. Then comes the list of inputs. In this case, there are two of them. They are called A and B, and they have the same type, namely they are square matrices of integers with p rows. Notice we use the variable p instead of n here to illustrate the issues that we discussed in the previous segment. This is a dummy variable. It could have been called n or q or r. The issue with picking the name n is that n is also the name of the input size in f of n, that is the time complexity. So to try and distinguish the two, I decided to use the name p here. Let's see if that helps. And let's not forget, the header line of the pseudocode must also indicate the return type of the algorithm. And of course, this function returns a matrix, a square matrix of size p by p. So remember, the algorithm or the definition of the problem requires that we go through all of the elements in A and add to them the corresponding element in B and store the result in the corresponding element in C. So we're going to have to go through all of the elements in each matrix. Since a matrix has two dimensions, we're going to need a nested for loop. And by convention, every time we have to go through all of the elements of a square matrix, we're always going to start by going through the rows. So the outer for loop will go through the rows, number 0 through p minus 1, and we're going to use the loop variable r to remember that we're going through the rows. For each row, we're going to go through all the columns, so we use the loop variable c, which will go from 0 to p minus 1, since there are p columns. Now, for each row and each column, we are going to compute the element in matrix C at that row index and that column index to be the sum of the two corresponding elements in matrices A and B, as we just explained. When we're done with this nested for loop, matrix C is complete and we can just return it. So this is the pseudocode for this algorithm for matrix addition. Now let's start the analysis of the time complexity of this algorithm. As always, we must define the size of the input to the algorithm. Well, this algorithm takes two matrices, but these two matrices have the same size, which is defined as p by p. So we only need one number to determine the size of the matrices, since the matrices have the same size. And for each matrix, since they have the same number of rows and columns, we also need just one number to determine the size of a square matrix. So we're going to choose as n the size of the input to the algorithm, the number of rows in each matrix. Notice now P is the actual number of rows, and we're going to take that number to be equal to n, which is the size of the input. Of course, we could have chosen P squared to be equal to n, but that's a different analysis which I'll let you do at home. Okay, now that we have defined the size of the input, we can decide which primitive operations we're going to count for the time complexity. So let's go through the pseudocode and determine all the primitive operations that are included in the algorithm. In the first for loop, we have an assignment statement. We have a comparison as well. Remember, R must be compared to P minus 1 every time through the loop. And of course, we have an addition. Since we have to increment R by 1, we also have an addition in this for loop, and we also have an addition in the body of the inner loop. So these are the three possible primitive operations we could count. As before, we decide to choose the additions. So the time complexity of this algorithm will be determined by the total number of additions that the algorithm executes for an input of size n. So what is the worst case time complexity of this algorithm? Remember, we're going to call this complexity f of n, where n is the input size. So what we need to do is to count the total number of additions that the algorithm performs for an input of size n. Let's start at the outer loop. We're going to first compute the total number of additions for one execution of one iteration of this outer loop. So initially, R is equal to 0. So what happens in that single iteration? Well, what happens is a complete execution of this for loop. So all we have to do now is to compute the number of additions in this one execution of the inner for loop. Now, how many iterations does the inner loop execute? Well, the answer is P. So we have P iterations. And for each iterations, how many additions are performed? Well, there's one addition right here, but remember, there's also one addition in the loop overhead to increment C. So we have 2 additions per iteration of the inner for loop, and we have P iterations. So we have 2 times P additions when R is equal to 0. Let's record that. The number of additions is 2 times P. Now, we look at the next iteration of the outer loop where R is equal to 1. Well, it turns out the same thing is going to happen in terms of additions. We're going to have P iterations of the inner loop and 2 additions per iteration. So when R is equal to 1 in the outer loop, the total number of addition is again 2 times P. And so on and so forth as R is incremented by 1 every time. For the last iteration where R is equal to P minus 1, according to the same reasoning, the total number of additions is equal to 2 times P. Now before we go ahead and start adding up all of these numbers, we should realize we forgot some additions. For every iteration of the outer loop here, there is an addition done to increment the value of R at the end of the iteration. So what that means is, for example, when R is equal to 0, there's one more addition here to do at the end of the iteration. And the same for the second iteration and for every single iteration until the last one. So now that we have accounted for all of the additions, we can go ahead and do the addition. We have 2p plus 1. We have p lines, so we have p times 2p plus 1, which of course is equal to 2p squared plus p. Now remember, when determining the time complexity of the algorithm, the input is called n, and n is equal to p, so f of n is just 2n squared plus n. And of course, we know from our previous study that this function is big theta of n squared. So in other words, the matrix addition algorithm is an n squared time algorithm. The last observation about this algorithm is that when we studied its time complexity, we never made any distinction between a worst case or a best case, because notice these nested loops always have to be executed completely. There's no way of short-circuiting or exiting the loop earlier than when they are completed. So in other words, every single case of size n is identical. There are no best cases, there are no worst cases, which means what we computed here is not only the worst case time complexity, but also the best case time complexity, and as a result, it's also the average case time complexity. This is one of these algorithms that has a single time complexity.